Good evening, everyone. First of all, it's our pleasure to have had the chance to participate in this conference. I'm Sarah Boudouh, PhD student in University of Lagouad's Lab, Algeria. We will have a sneak peek to our work titled Breast Cancer, Breast Tumor Detection in Mammogram Images Using Convolutional Neural Networks. Female breast cancer has now surpassed lung cancer as the leading cause of global cancer incidence in 2020, with an estimated 2.3 million new cases, representing 11.7% of all cancer cases. Among women, breast cancer accounts for 1 in 4 cancer cases and for 1 in 6 cancer deaths, ranking first for incidence in the vast majority of countries. Breast cancer can be detected using several imaging techniques. Mammogram imaging is the most often used technique to identify suspicious lumps in the breast. It allows radiologists to detect abnormal masses. Yet still, it is difficult to interpret the mammogram since lesions detection in it depends on radiologist's level of experience and also on image quality, which leads to diagnostic errors. The increase of abnormalities detection failure in the mammogram is due to the poor image quality, eye fatigue, or oversight by radiologists. Thus, it is needed now to assist doctors in diagnosing and detecting breast cancer, which will help to speed up the diagnostic process. In our presentation today, we will see some state-of-the-art. We're going to after that present briefly our approach, and finally we will have a conclusion. So in the topic of breast cancer detection and diagnosis, there has been a lot of research published. However, we will focus on those that did the detection using mammogram images, which can be divided into 3 categories. First, we have breast tumor detection, which is a binary classification of normal and abnormal mammogram images. Second, we have breast cancer detection, which is a multi-class classification where the classes are normal, benign, and malignant. And finally, we have a breast cancer detection. It is also a binary classification, but just for tumor cases, so the classes are benign and malignant, which is out of our topic today. In order to confirm the presence of a breast tumor, a binary classifier containing normal and abnormal mammography is required. To do so, the model must be able to distinguish between normal and abnormal breast tissue. Thereby, the region of interest in this situation is the whole breast. On the other hand, in order to detect the tumor's type using a binary classifier with benign and malignant mammogram images, the ROI in this case is the tumor area, so we don't need the whole mammography as an input. Hence, to have a breast cancer detection model with great accuracy, we need to have a solid step 1 with a high accuracy, which is in this case a tumor detection model. Then, we can have a new one that is built based on the first model for tumor type detection. This was the main limit of several previous works where they addressed the problem with the multi-class classifier. So, we aim to propose an accurate breast tumor detection model as a first step into cancer detection. And according to the preceding, in our proposed study, we found that instead of using just the commonly used database, which is the Mammographic Image Analysis Society Mini Mammographic Database, we can take more samples from a different one, especially that the abnormal class has less number of images than the normal class, in order to guarantee diversity in the images and in the same time balance the data, which leads to a well-trained model. So, in our approach, first of all, as mentioned before, we gathered data from 2 databases to avoid the problem of imbalanced data, which could affect the accuracy. The first one was the Mammographic Images Analysis Society Mini Mammographic Database. Taking all the database as a sample will be 207 normal images, 115 abnormal ones, including benign and malignant cases. That will make the total of 322 mammogram images. And the second one was the Chinese Mammography Database, CMMD, which include just abnormal cases, where 92 abnormal images mixed benign and malignant were added as a sample from this database, covering the shortage of images in the abnormal class. That made the total number of images in each class equal. The gathered mammogram images were pre-processed using several filters in order to extract the region of interest, which is in this case the breast area, and remove the noise as well as the background. First, the binary filter was applied to the images, as you can see in example from each one. Then, the resultant image was used to detect the largest blob, which is the breast area, and by multiplying the new resultant image with the original one, all noise will be eliminated and we get only the breast. But since the CMMD images doesn't have any noise except the background, the process was easier there. Next, we have the Wiener filter, which we consider as a noise removal filter. Using it allows us to eliminate any remaining noise. After that, the objective of contrast enhancement is to improve the imagery low contrast of masked pixels. Therefore, it is used on images that include abnormalities. To accomplish that, we use the contrast limited adaptive histogram equalization Clahy filter. After that, the data was split randomly into 75%, which is 310 images, 155 images per class as a training set, 5%, which is 20 images as a validation set, and 20%, which is 84 images as a testing set. To guarantee accurate evaluation, we reduce the amount of data in the validation set and add it into our testing set. Next, the data augmentation technique was achieved through simple modifications such as horizontal flipping, zooming, and so on. We use it on the training set. And then the training process starts using a proposed CNN. The suggested convolutional neural network architect was inspired from the AlexNet pre-trained model. It includes 4 convolutional layers, each one followed by a max pooling layer, one flattened layer, a dropout, a fully connected layer, and a sigmoid output since the classification was binary. Finally, the model was evaluated to determine how accurate it is using the testing set, and the obtained results were compared to the previous studies. We were able to determine the accuracy, sensitivity, specificity, and the area under the curve based on the results from the confusion matrix and the ROC curve, as you can see in the figures. From the obtained results, we can declare that we accomplished our goal by creating an accurate breast tumor detection model as well as proving the ability of our proposed preprocessing phase. However, when compared to previous studies, especially the works which were in the same context of our work, our results were way better, as we can see, even with those who used transfer learning techniques. So to sum up, the results of this study shows an accurate breast tumor detection model which proves that our approach was useful. We managed also to prove that one of the reasons that could increase the accuracy is the input image, and especially the region of interest in breast tumor detection and tumors type detection is not the same, and each problem should be treated separately in order to achieve better results, as well as balancing the data in each class will help to improve the accuracy more. Accordingly, the chosen filters in the preprocessing phase were well suited to our situation, putting our approach ahead of the existing ones. For the future perspectives, first, adding another database to the collected dataset may have better results since using 2 achieved great ones. The same thing with the filters. We can add more filters in the preprocessing phase. Second, we can test our preprocessing strategy with transfer learning techniques by adapting a pre-trained model such as the VGGs, the ResNets, exception, and others. That may improve and validate the approach more, since it was just tested on a proposed CNN model. And finally, and the most important, since the obtained model was accurate, it could be useful as a solid first step for identifying the specific type of abnormalities, such as benign and malignant. It dives even further into the subtype of a single kind, like masses and calcifications. Therefore, we can assert that what we accomplished could be used as a starting point for future research. This could help achieve better results in breast tumor type detection, and that leads to an accurate computer-aided diagnosis systems for breast cancer. Thank you for your attention. Happy to answer any of your questions.